Hello, our video today introduces our Excel add-in for ideal flow developed by Dr. Cardi Technomo and delves into the topic of the stochastic matrix in relation to the ideal flow. This video is part of a series of tutorials on research output and graph theory related to transportation science. It's recommended that you watch the previous video in the series entitled Ideal Flow on Network. You can click here to be redirected to the video, or you can click on the link in the description. Rather than manually simulating a random walk every time, we can compute for ideal flow given capacities or capacity ratios through the Excel add-in that we have developed. The Ideal Flow Excel add-in can be downloaded from the link in the description. It contains the add-in and the PDF file that contains instructions on installation, specifications, and use. Now that we've installed the add-in, we can start. Let's use one of our road networks from last time. For this road network, we only know its interconnectivity structure and not how many lanes it has, so we'll assign a capacity of 1 to each road. That means if we don't have information regarding the capacity of each road, the best assumption is to give them relatively the same number of lanes. Regardless of the actual number of lanes, what we need here is simply the relative comparison of the number of lanes between length. We put 0 when there isn't a road there. Remember, in the matrix, rows represent your starting nodes and columns represent your end nodes. So cell B3 would be a road going from node 3, the office, to node 4, the park. Now that we've inputted all our values, right-click the top left cell of your input, and at the very bottom, you should see ideal flow. Click Calculate. Okay, here appear the results. These are the ideal flow for the length given the capacities that we entered. You'll see that we got the same result as in the previous video. Let's explore the add-in a little further. Right-click once more. When you click About Ideal Flow, a pop-up will appear. This is the definition of ideal flow, and if you click Help, it will open the PDF document that came with the add-in. If you click Random Example, it will give you a random example of a matrix of capacities and its corresponding ideal flow. We'll go back to this later. Now let's click on Setting. Let's do this tab by tab. The first tab is Settings. You can set where the top left cell of the matrix you want calculated is located, how many nodes your network has, and where you want the output to be placed. There is a limit of up to 25 nodes. Now to Scaling. Remember that the random walk generates large numbers. We want to scale these down to manageable numbers. There are different ways we could do that, and we'll discuss these 4 options in a future video. For output, we can choose what optional output we want displayed. We'll discuss these in future videos. Now let's move on to random example. We saw earlier that we could generate a random network, and this add-in gives us 3 kinds of matrices to choose from. Notice that currently, adjacency matrix is selected. This is the simplest type. An adjacency matrix simply tells us which nodes are connected. We designate the links to those nodes as 1, which also stands in for their capacity of 1. If they aren't connected, we put 0. Normally, for adjacency matrices, we would put a 2 if there were a loop connecting the node to itself, but we assume that there are no self-loops in our road networks. Now, the next option. We can generate an example with a stochastic matrix. Where there were only 1s and 0s before, we see now that we have ratios. A stochastic matrix is a matrix of probabilities, used to describe the transitions of a Markov chain. A Markov chain is a model of some random process that happens over time, which follow a rule called the Markov property. The Markov property says that whatever happens next in a process only depends on its current state and has no memory of the states before. Specifically, this option will generate a right stochastic matrix where the probabilities in each row sum up to 1. Since all cars that enter the node will have to leave it, 1 or 100% is the probability of them leaving the node. When there are many roads in which they could exit the node through, the probability describes how likely they are to go through that road. So when we generate a stochastic matrix, rather than using capacity, we're using probabilities. Let's use this matrix we've prepared. Let's turn it into a network graph. Since this is 1, it means that all cars that go through this node have a 100% chance of taking this road to go into the next node. This one could perhaps indicate a left turn, a right turn, and a 2-lane straight. Agents have a 25% chance of going left or right and a 50% chance of going straight. From here, they have 2 ways out. Notice that they're not 50-50. Cars have a 56% chance of going through this road and a 44% chance of going through here. This could be because of better roads, because slightly more people go to the first node than to the 5th node, etc., etc. Another road with 100% probability. Finally, 3 roads with equal probabilities. Cars are equally likely to take any of these 3 roads. You can see that this is more general and more useful than simply an adjacency matrix because it allows you to give weights to the roads, as not all roads have the same capacity in real life. This will allow you to model ideal flow for your road network more accurately. The downside is that gathering the data required to assign these probabilities is difficult. These probabilities can be approximated by measuring the trajectories of vehicles that take the road for some amount of time. We'll discuss 5 major methods to gather the data: through GPS, cameras, cell towers, inductive sensors, and manual counting. The first 3 methods, GPS, cameras, and cell towers, are considered Intelligent Transportation Systems, or ITS. We will discuss ITS further in a future video. Built-in GPS in cars and phones may be used to obtain the trajectories of vehicles with good accuracy and a good amount of data. The most accurate GPS devices are quite expensive, however. GPS in phones are not as reliable as those in cars, but will do as well. This data may be obtained from car manufacturers, from public vehicle operators, such as transportation companies of taxis and buses, or from mobile applications that gather data on the movement of vehicles, such as navigation applications like Waze, or ride-sharing applications like Uber. Cameras, meanwhile, may be placed on the intersections of interest, and through the video produced, the vehicles that turn in the intersections may be identified through vehicle recognition software. Just knowing how many cars pass through one section of a road is insufficient, so you would also have to know where they're going. Cameras may be used to measure turns and match the amount of vehicles that pass through a road segment. The cell phone signals of a person inside vehicles passing through the roads may be determined through cell tower triangulation, although this is less accurate than GPS data. The data would also have to be obtained from mobile network carriers, and there may be restrictions that come with this. Another would be inductive sensors. Once placed under the road, they detect, through electromagnetic currents, vehicles that pass over it. It can count the vehicles that pass through the road. However, this can be problematic. Installing wire loops would require construction on the roads, and when modifications to these roads are made, such as re-asphalting, the sensors would have to be recalibrated as well. Finally, there's the option to manually count each vehicle that passes through the road, and which way they go. Depending on the amount of roads, the sizes of the roads, and the amount of vehicles that traverse the road, this would require a lot of manpower. While it already seems daunting to use one of these methods, generally they must be used in combination to calibrate the results. We will go into even further detail regarding ITS in a future video, but for now, we can see the difficulties encountered when gathering data for traffic flows. So while the use of probabilities to stand in as capacity ratios allows for greater accuracy, this is because you also need great amounts of data to determine these probabilities. It's always possible to come up with rough estimates, of course, for the trade-off of accuracy. And for our convenience, we can always generate a random example from our ideal flow Excel add-in. That's it for today. In the next video, we will discuss our next type of matrix, the capacity matrix. I hope you enjoyed this video tutorial. You can also visit other tutorials from Dr. Cardi's website, people.rivaledu.com/Cardi, and the Ateneo Pedestrian and Traffic Computing Laboratory, pinoy.admu.edu.ph/-pedlab. Thank you for watching.